Hello guys, how are you doing? Fromage here. Today I want to solve this integral. Is the integral from 0 to infinite of e to the minus x squared over x of times sine of ax dx. So let's get to it. So I will do the following. I will expand the sign as a series. Yeah? So this integral will be equal to the integral from 0 to infinite of e to the minus x squared over x. And now the Taylor series of the sine of ax is equals sum from n equals 0 to infinite of minus 1 to the n ax to the 2n plus 1 over 2n plus 1 factorial. Yeah? Now I will take out the constant terms that don't depend on the sum out of the integral, the constant terms that don't depend on x. So I equals, will exchange integration with summation, sum from n equals 0 to infinity of n to the minus 1 over 2n plus 1 factorial. We can take the a also outside of the integral, a to the 2n plus 1. Then we have integral from 0 to infinity of e to the minus x squared. We have here an x that we combine with this 2n plus 1 to x to the 2n plus 1. So we will just get x to the 2n dx. Yeah? Now this integral, we will do the following change of variable. Yeah, we will say u equals x squared. Yeah? Or the same, x equals square root of u. Yeah? The variable, not u. Then the integration limits it will be the same. We now just need the differential of x. Yeah. So from here we get that dx equals du over the 2 and the square root of 2. Yeah. So now we will replace again, and we get I equals sum from n equals 0 to infinity of minus 1 to the n over 2n plus 1 factorial a to the 2n plus 1. Yeah. We will take out the 2 outside also from here. So we get the same integration limits of e to the minus x squared, but the minus x squared is u, minus u. X to the 2n is now is just u to the n. Yeah. And we have the differential, the u over the square root of u. Yeah. So this integral we can combine the u to the n over the square root of u equals u to the n minus 1/2, or the same as u to the n plus 1/2 minus 1. Yeah? So this integral here will be just integral from 0 to infinite of e to the minus u to the n minus, plus 1/2 minus 1 du. And this is just the gamma function. Yeah? gamma of n plus 1/2. Yeah? So our integral, original integral, equals the sum from n equals 0 to infinity of minus 1 to the n over 2m plus 1 factorial a to the 2n plus 1 over 2 times gamma of n plus 1/2. Yeah? So I will get another paper. Just a second. So now we need to express our gamma function in a simple way. Yeah. So we have to evaluate gamma of n plus 1, where n is an integer more larger or equal than 0. Yeah. So this can be done with something called the Dublin formula. The Dublin formula is the following: is gamma of n times gamma of n plus 1/2 equals the square root of pi times gamma of 2n over 2 to the 2n minus 1. Yeah. So we can get from here that gamma of n plus 1/2 equals square root of pi times gamma of 2n over 2n minus 1 over gamma of n. Yeah? So this will be the same as square root of pi. As n is an integer, we can write this as in a factorial form. So this will be 2n minus 1 factorial over n minus 1 factorial. Yeah? So, and now we can multiply and divide by n. So this will be equal to square root of pi over 2 to the 2n times 2n minus 1 factorial over n times n minus 1 factorial. Yeah? And this is equals the square root of pi over 2 to the 2n times 2n factorial over n factorial. Yeah? So, and this formula now is valid for n equals 0. Yeah? So we can check that if we replace n equals 0, we get gamma of 1/2 equal the square root of pi. Yeah? So we are good. Now we will replace this formula in our original integral. So we get another paper. Our original formula was I equals the sum from n equals 0 to infinity of minus 1 to the n over 2n plus 1 factorial a to the 2n plus 1 over 2 times gamma of n plus 1/2. But we found that this is the same as the square root of pi times 2n factorial over 2 to the 2n over n factorial. Yeah? So, this is the same, again, as the sum from n equals 0 to infinity of minus 1 to the n. Here, this term, the 2n plus 1 factorial, will get almost all terms cancelled except the 2n plus 1 with the 2n factorial. So we get just 2n plus 1. Yeah? And we can combine these 2 with this other 2n, 2 to the 2n. So we can get a over 2 to the 2n plus 1. Yeah, also combining with the a. And finally, we got this n factorial. Yeah. So for now, we can see that this seems like an integral was taken here, because we have 2n plus 1 in this exponent, and we have 2n plus 1 in this denominator. So we can also write this as the I equals the sum from n equals 0 to infinity of minus 1 to the n over n factorial times the integral from 0 to a over 2 of x to the 2n. Yeah, dx. Yeah, if you make this integral, you get this term over this 2n plus 1. So now we will exchange the integration with the summation. So we get the integral from 0 to a over 2 of, sorry, I forgot the square root of pi here. Square root of pi, square root of pi here also. Square root of pi. And here we have the sum from n equals 0 to infinity of minus 1 to the n over n factorial times x to the 2n. Yeah? This here is clearly the Taylor expansion of e to the minus x square. Yeah? Yeah, can you recognize? So, finally, we get that I equals square root of pi integral from 0 to a over 2 of e to the minus x squared dx. Yeah? Or we can write it in another way. Square root of pi times square root of pi over 2 times 2 over square root of pi integral from 0 to a over 2 of e to the minus x squared dx. Yeah? And this is called the error function. Yeah! Yeah, so finally our integral I equals pi over 2. I multiply the 2 square root of pi and error function of a over 2. Yeah, and that's it. Okay, thanks for watching. I hope you like it. See you!